So, as we talked about last time, what happens in a realistic situation is pretty much all oscillators are damped. They're going to be damped in one way, either under damping, critically damping, or over damping. That depends on the particular system. But basically what happens is, again, in any realistic situation, in this harmonic oscillator, if we leave it alone, it will eventually stop. So for example, if I set a spring mass system oscillating in this room, it's going to stop because even if it's something which is oscillating vertically, it's in a fluid, and that fluid then is going to apply some sort of damping term to it since it's moving relative to the fluid, meaning that there, as we talked about in chapter 2, I think it was, when we have something moving in a fluid, there ends up being some sort of velocity-dependent damping term, which is going to cause the energy to go away. So if we want our oscillator to keep moving indefinitely, basically forever, we're going to have to put energy back into the system, which is what we call drive it. So we're going to have to drive this harmonic oscillator, causing it to keep moving, even though energy is being lost from the system. So we then want to analyze this particular situation. So let's say that we have our, say, spring mass system. So here's my spring mass system. So again, this is going to have the spring force acting on it, say in this direction. Say it's moving this way, so this is the direction of x dot. So we're going to have our damping term then in this direction. But we're also going to try to force this thing to keep moving. So we're going to apply a force on here, which in most cases is going to be some sort of time-dependent force to keep this thing actually moving. So from Newton's second law, we can then write that what? The mass times the second derivative of the position is then equal to, so in this case I get what? Minus my damping term, so some minus b times dx dt. I get the spring force, I get minus k times x, but I get this extra driving force which is going to try to push the thing into keep it from moving, or keep it moving. Now, let's divide everything by m and rearrange everything. So in this case, we can rewrite this then as what? So it's going to be the second derivative with respect to position plus twice of beta times dx dt plus omega 0 squared times x. So all this is our damped harmonic oscillator. But all this then is going to equal little f of t, where we're defining that little f of t is going to be big F of t per unit mass. So this is the driving force per unit mass. So this is the second differential equation, second order differential equation that we want to solve. As we can see from here, this is an inhomogeneous second order differential equation, because here, if this whole entire thing was equal to 0, then that would be the homogeneous differential equation. But it's not, it's equal to some function. Because of that function, this thing is then inhomogeneous. Now, we can actually relook at this left-hand side and think about this in a different way. So what I could do is I could define what's called a differential operator, and I could actually write my differential equation this way. So what I could say then is I have this differential operator d acting onto my function x, which is then generating a new function of f of t. So here, we're defining this differential operator as then being the second time derivative plus then twice of the damping coefficient, or the damping parameter, times then the first derivative plus then omega 0 squared, which again is that natural frequency. So this is what we call a differential operator. So why is it called a differential operator? Well, first of all, it's an operator because it operates onto something. So what does that mean? So basically what that means then is this differential operator acts onto a function to then generate some sort of new function. Or if you want to think about this in a different way, what you're doing is you're starting off with some sort of space, which is defined by the function x of t. Then by acting on this differential operator, you're now transforming this function into a new function, which is defined by this new function f of t. So this is actually what a differential operator does. So it's an operator which then acts then onto some sort of function, which then generates a new function, or it's a mapping from one space to another space. Now in physics, we use differential functions all the time. One, for example, is quantum mechanics. In quantum mechanics, what we simply write is that the Hamiltonian acting onto the wave function then is equal to the energy times the wave function for, well, in this case, this is what we call the stationary phases or the steady state situation, or more in general, this becomes equal to I times the partial derivative with respect to t acting then onto the wave function. But anyways, H then is a differential operator because it depends on the derivatives, as this thing does. So it's a differential operator because it depends on derivatives. But again, ultimately what that does is it takes our function and then maps it from one space to another space, which basically just changes this function. Now, the nice thing about differential operators is they satisfy particular properties, and those properties have to do with linearity as well as superpositions. So, for example, some properties are, if I took my differential operator and I acted on to a constant times a function, where a in this case is simply equal to a constant, let's say this is equal to a real number, then this thing is simply equal to that constant times then a differential operator acting onto the function. Another one says that if I have a differential operator acting onto two functions, say x1 plus x2, then this thing then is equal to the differential operator acting onto the first function plus the differential operator acting onto the second function. And then finally, if I have the differential operator acting onto some constant a times x1 times some constant b times x2, then this is equal to a times dx1 plus b times 2dx2. So ultimately all this says is that what? If I have two functions which satisfy this second order differential equation, then by adding in these two functions with particular coefficients, then the sum of those is simply a solution of this original differential equation. That's all this thing says. So it's simply talking about superposition. So if I have, for a second order differential equation, if x1 and x2 are both solutions of that original differential equation, then so is the sum of x1 plus x2 with some sort of coefficients, or in this case, simply these two. So this, you imagine this is the same thing then as d of x3, right? Where x3 is simply the sum of those two different solutions of this differential equation. So good. So let's go back to our differential equation that we have to solve. So again, here we have simply that's what? Our differential operator acting onto our function that is equal to some new function. Now again, this is an inhomogeneous differential equation. When we first saw these in class, we talked about those. What happens is that the solution gets broken up into two parts. One part is what's known as the homogeneous part. The other part is what's known as the particular solution. So here, our homogeneous solution is simply equal to 0. So this is when the differential operator acting onto the homogeneous portion of our differential equation is equal to 0. Of course, we spent the entire last lecture talking about this. This is simply our damped harmonic oscillator, so we already know what the solution of this is. The particular solution then is when our differential operator acting on a particular solution is then equal to that function. So that the total solution then, so x total, or we're simply going to call x, is then the sum of the homogeneous part plus then the particular parts. Right? Now, based on what we just saw then with the linearity or the superposition conditions then for the differential operator, all this means then is that d acting on x then is the same thing as d acting on x homogeneous plus x particular, which is the same thing as dx homogeneous plus dx particular. But we know the solution for this one is 0 plus f, which is simply equal to f. So all this says then again is that we can split this up then into the homogeneous part plus the particular parts to then solve for the solution of our differential equation. So all it means then is to find the solution for this damped driven harmonic oscillator. We already know the homogeneous solution. All we then need to do is know exactly the structure of what this driving force is, or in this case, the driving force per unit mass, to then determine what is the solution overall for this particular differential equation. So let's use this and let's do a particular example just to kind of see how this works. And the example we're going to look at is the sinusoidally driven oscillator. So let's say that our function f of t is equal to some constant, let's just call it f0, again that's the force per unit mass, times then cosine of omega t, where omega then is the driving frequency. So again, this thing is sinusoidally changing, causing this thing to move. And then this is the frequency at which this thing is being driven at. Now, from here, we would simply plug this in and then try to solve for a particular solution. Now, in case of sines and cosines, this actually turns out to be rather difficult. It's actually kind of an annoying way to solve it, if we would do it that way. So another way to do it is actually to use something we talked about a little bit earlier, which is complex variables. So here, an easier way to do this is actually to note that, using, again, Euler's theorem. So Euler's theorem says that e to the I theta is then equal to cosine of theta plus I times sine of theta, which means that cosine of theta is simply equal to the real parts of this exponential. So from here, if I take the real part of e to the I theta, well, that's simply equal to cosine of theta. So here, what we're going to do then is actually complexify f. So here, if you want to think about this as f tilde, which depends on time, we're going to rewrite this then as some coefficient, f tilde, which most time actually we don't even have to do, let's just leave that as f, times then e to the I omega t. So in this case, f of t then is simply equal to the real part of f tilde of t. Okay? So basically, all we're going to do then is we're going to complexify f to make it into f tilde, make it a little bit easier to solve, because now it's a lot easier to solve for exponentials as opposed to cosines and sines. And then at the end of the day, we're just simply going to take our real part of our solution that we find for this complexified function, and then that's going to be the solution to our original differential equation that we want to solve. Okay? So having said that, what we want to do then is rewrite x as z, because traditionally we think of complex variables as z. So with that, we're going to rewrite our new differential equation as then being what? Our differential operator acting onto z then is equal to f tilde of t. So this is now the differential equation that we want to solve. Now again, we already know the solution for the homogeneous portion, so in this case we simply want to look at the particular solution for this. And again, once we find a particular solution for the complex version, we then take the real part to then find the real portion of this guy. Okay. So good. So let's do that. Now, so here, all this means then is we want to take our differential operator. Zp then is equal to f0 times e to the I omega t, where d is defined as before. Now, in this case, since the right-hand side is proportional to e to the I omega t, what that means then is that we should expect our z of p, our particular solution, equal to some constant, let's just call that guy c, e to the I omega t. From here, we're going to plug this into this expression to then determine exactly what this coefficient is. Now, the nice thing about that is because now we're taking derivatives, we're going to have simply an algebraic expression to solve for that coefficient. So let's do that. So let's take this ansatz here for our particular solution, and then simply determine what that coefficient is. So good. So let's do that. So let's remind ourselves our differential operator becomes the second time derivative plus twice of beta times then the first time derivative plus omega 0 squared, all times then some constant e to the I omega t, and we want that equal to some f0 tilde e to the I omega t. So good. So c is simply a constant, so it's going to pull through. Now let's take some derivatives. Take a second derivative. I'm going to get down I omega, that one-sided quantity squared, which is simply minus omega squared. Get this part, take a derivative that brings down an I omega, so I get plus 2I beta omega plus then omega 0 squared, nothing happens to that, all times my exponential, e to the I omega t, and all that's equal to f of 0, e to the I omega t. Now, for now, I'm going to drop that tilde portion because, again, turns out it's actually a real variable anyways, but that's fine. So the e to the I omega t's are going to cancel, and then from here, I'm simply going to solve for C0, or for C. So this tells me C then is equal to F0 divided by omega 0 squared minus omega squared plus twice of I beta omega. So this is my value of C. Now, this guy is complex because I have a I here. So one way we can always rewrite a complex variable, as we talked about in the last lectures when we talked about Hooke's law when we originally solved this, is we can think about this as a real part with an imaginary part, or we can write it in plane polar coordinates by thinking about what? So this is C, so I have the real part of C, and then have the imaginary part of C. This is going to correspond to some value, say here. So I can then rewrite this then as the magnitude of C, which I'm going to call simply A, times this angle here. Okay. So I can always rewrite it this way. So I can rewrite C then as being equal to A, which again is equal to the magnitude of C, times e to the I delta, where delta then is what? Going to be given by the tangent of then the imaginary part divided by the real part. So tangent of delta then is going to be equal to what? The imaginary part of C divided by the real part of C. So we'll figure that out in just a second. So first off, we need to determine what A is. So let's determine A. So again, A is simply going to be the magnitude of C. So A then is equal to the magnitude of C. Well, it turns out the magnitude of a vector, or at least an imaginary number, is the same thing as the square roots of C times C star. So basically what we're going to do is we're going to multiply top and bottom, or multiply C by C star. Again, when I take the star, all I'm going to do is I'm going to change this part here to then a negative I instead of a positive I. So if I multiply this out, take a square root, this thing ends up being then F0 divided by omega 0 squared minus omega squared plus 4 times beta squared times omega squared. So that's this guy. Now, delta, again, is given by the fact that we have tangent of delta then is going to be the imaginary part divided by the real part. Well, to turn this then into a real variable, what we'd usually do is we multiply top and bottom by C star. Basically, the reason that we would do that is, again, we want to get rid of this imaginary part in the denominator and basically put it in the numerator. It's much easier to determine what that is. Well, if I multiply top and bottom by C star is just going to make the denominator equal to this denominator. But on the top, I'm going to have the real part and then the imaginary part. So in this case, the imaginary part then is simply going to be this, and the real part is simply going to be this. So this is going to be equal to 2 beta omega divided by omega 0 squared minus omega squared. And again, I'm doing that because the real part is going to have this term for the denominator. The imaginary part is also going to have this part for the denominator. So when I divide them, that portion is going to go away. They're both going to have an F0 to them. That portion is going to go away as well. So it's simply going to be this guy. So good. So from here, this tells us then that our particular solution then was equal to what? C e to the I omega t, but that's going to be the same thing as A e to the I delta times e to the I omega t, which is the same thing then as what? A e to the I omega t plus delta. So that's this guy. So this is our solution. This is our particular solution. Now again, what we want is the real portion of this. So we're simply going to take the real portion. When I take the real portion, this part is simply going to be what? A still, because that's a real variable. Here I'm simply then going to get cosine of omega t plus delta. So finally, from this, we can then learn that the particular solution, which again is equal to the real part of the complex version, is then equal to A times cosine of omega t plus delta. So good. So this means our total solution, which again is a homogeneous solution, plus then the particular solution, is then equal to C1 times then e to the I, or sorry, not I, e to the lambda plus times t, plus C2 times e lambda minus times t, where again these guys are the eigenvalues from the original differential equation, the homogeneous one, but again, what this thing looks like is going to depend on the sizes of omega 0 versus beta, which gives us the different overdriven versus underdriven, or overdamped versus underdamped versus critically damped, plus A times then cosine of omega t plus delta. So let's talk about what's happening here. So what's going to happen then is what? At early times, these terms are going to be important, but overall I'm going to get this harmonically oscillating term. So basically the particulars of how this thing looks at for early times, so if I wanted to plot the solution versus time, how this thing happens for early amounts of time is going to be dependent on what this thing is actually doing. So meaning it's going to be dependent on, is it underdamped versus overdamped versus critically damped? And overall, what are these coefficients doing, right? So here, this is going to be complicated, which depends on the type of damped oscillator. But let's continue to look at what happens. So what also happens, though, as you can see from here, is what? As time increases, what we know is that, what? These two things are going to be exponentially damped, which basically means that for the damped harmonic oscillator, regardless of what type it is, meaning for the overdamped, underdamped, or critically damped, these terms are going to go to 0. So as time goes on, what ends up happening is these terms go to 0, leaving only this term. Now this is kind of interesting. So basically what this says is that, what? Regardless of what type of harmonic or damped harmonic oscillator this thing is, that's going to determine what happens for the early times, but for late times, all three of these different possibilities, the overdamped, underdamped, and critically damped, will all decay exactly into just this driven harmonic oscillation, meaning it's going to be oscillating at exactly this driven term. Okay? So basically, whatever happens here will eventually just become this, okay? Where the amplitude of this thing is simply A, and this thing is going to be oscillating with a period, where that period then is determined by 2 pi divided by the driving frequency at which this thing is oscillating. So these terms here are what are called transient terms. Because what happens is, even though they determine what's happening for early times, these things are simply going to die out and then go to 0. And then we're left with simply just this driven oscillator. So again, no matter what type of oscillator we start off with, at least what type of damped harmonic oscillator we start off with, they all approach this same situation here. Now, again, what's happening here is going to be dependent on the initial velocity, going to be dependent on the initial position, it's going to be dependent on beta versus omega, all those different things. But again, as this thing goes off, as time approaches infinity, and for late times, all three of these different situations will all congeal to this just particular harmonic oscillation, which is determined purely by how this thing actually oscillates, based off of this sinusoidally driven oscillator. Now, for particular values of omega, this thing will have different values of A. So remember, A was dependent on omega in 2 different places. So let's rewrite what A is. So again, A was equal to what? F0 divided by omega 0 squared minus omega squared plus 4 times beta squared omega squared. So basically, for different values of omega, A is going to be different values. So what does that mean? So basically, the amplitude of the oscillation then will be dependent on the relationship between the natural frequency of this harmonic oscillator versus that of the driving oscillator. So in this case, we can see that if omega is very large, what will happen is that the denominator will become very large, which is going to drive the amplitude basically to 0. So if I'm driving this thing with too big of a frequency, basically that's going to destroy basically the oscillation, which is going to cause the amplitude basically to go to 0. But as the frequency then decreases, what will end up happening then is that I can have a point where this amplitude will then go to its maximum value. So to find out where that's going to happen, we can simply take A here and differentiate it with respect to the frequency and evaluate that as what's known as the resonance frequency, where the resonance frequency is when A is going to have its greatest amplitude. It's going to be its biggest value. Or that's also equal to the derivative of C, evaluated at the resonance, because those two are basically the same. And we're going to set that guy simply equal to 0, and then from there we can solve for the resonance. So if we do that, let me skip some steps, but basically what we find is by doing this, taking this derivative, write out what the derivative ends up being. So this derivative ends up being minus f0 squared times 4 times the resonance frequency, times then the resonance frequency squared minus the initial frequency squared, or the natural frequency, times 8 beta omega r, all divided by the resonance frequency squared minus the natural frequency squared, quantity squared, plus 4 times beta squared times the resonance frequency squared, quantity squared. So setting this guy equal to 0, and then solving for the resonance frequency, what we find in this case then is that the resonance frequency ends up being plus or minus the square root of the natural frequency squared minus twice beta squared. So this is the resonance frequency. Now, notice this thing has a condition. So basically what happens is as beta gets bigger and bigger and bigger, this resonance frequency gets smaller and smaller and smaller, until the point where if beta, or at least twice of beta squared, exceeds the fact or the size of omega 0 squared, i.e. that natural frequency squared, what will happen then is that omega, or the resonance frequency, becomes imaginary, which means there is no resonance frequency. So basically all that means is if I have too much damping then will destroy any type of resonance, so I'll never actually be able to get some sort of resonance out of this thing. So to achieve a resonance frequency, i.e. to achieve the greatest amount of amplitude as possible, we then have to make sure that this term then stays smaller than the resonance frequency. I.e., what we need is that beta must be less than omega 0 divided by the square root of 2. That's the only way we're going to get a resonance frequency. If it's exactly equal to this, the resonance frequency then is simply at 0. So nice. So we can describe the degree of damping in an oscillating system in terms of what's known as the quality factor or the Q factor. So let's quickly talk about the quality factor and Q factor. So Q factor, pardon me, so much chalk dust in here. So Q factor is what we call Q. Q then is defined as the resonance frequency divided by 2 times beta. So again, one thing we can see here again is that beta becomes very large, i.e. there's a lot of damping. This term is going to go to 0, this term is going to become very large, or this term becomes imaginary, which basically means that Q is going to go to 0. So basically if there's a lot of damping, so for large beta, then Q goes to 0. And then if there's not a lot of damping, so for small, beta, what ends up happening in this case then is that what? Q is going to become very large. Is large. So to kind of understand what this thing is going to do, so let's say, well, let's make a quick plot. And here we're going to plot C divided by F0 on this axis. And then the angular frequency on this axis. And let's see what actually happens here. Let's talk about resonance in this case. So first off, if I have Q is going to 0, basically meaning that, again, B or beta is very large, so there's way too much damping. That's what's happening in this case is that basically this thing has no resonance. I'm going to look, say, something like this. As my Q factor then starts getting bigger and bigger and bigger, meaning that the damping becomes smaller and smaller and smaller, it's a lot easier then to have some sort of resonance. And in this case, we're going to get things that look like this. So for kind of a smallish type of Q value, this thing's going to do something like this. So in this case, this is going to be my resonance. So this is going to be Q of about something like 2.69. I can also have something like this. So a bigger Q. So I have bigger than resonance. In this case, Q is going to be something like 4.95. And then finally, let's do a green one. This thing's going to do something like this as Q then becomes bigger. And again, as the damping becomes smaller. So this is for a Q.83. So basically, draw this thing perfect, but that's fine. So basically what happens is, again, as Q factor gets smaller, that means that the damping becomes smaller, so we end up with a lot more resonance. So the smaller and smaller that Q or the bigger that Q becomes, pardon me, so the bigger that Q becomes, what happens in this case then is the height of this peak becomes larger, but what I didn't draw very well here is also that the width of this thing becomes a lot more narrower. So the smaller amount of damping will give us a lot more resonance. In this case, what will happen then is that you will get the biggest amount of amplitude, which again was what the resonance is. So the amplitude of the oscillation will become much, much, much bigger when the frequency is going to then match the resonance frequency, meaning that this thing is going to be driving with the largest amount of amplitude. So here, again, if I look at the amplitude, or at least at C, what happens here, again, is that the peak or the size of the amplitude is going to get much, 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 much bigger. But again, the width of this thing gets much smaller, meaning that you're getting much closer to this resonance frequency. Or again, this would be then my resonance frequency. Now, we talked about this in 206. What happens at resonance is all kinds of different things. So, for example, if I match the resonance frequency of my house, i.e. the natural oscillation at which the wood and things in my house is actually oscillating, happens in that case then is that the amplitude of the oscillation becomes so great that it would actually destroy my house. It would rip it down. This is what happened with the Tacoma Bridge. So again, the Tacoma Bridge, in that case, the driving frequency matched the resonance frequency. In that case, it dropped, right? In particle physics, this is actually a good thing, unlike the two examples I just said. So in that case, when the frequency then matches the resonance frequency then of the particle, you get a nice spike, meaning that the amplitude of oscillation is large. So in that case, you're actually creating the particle because you have enough energy to actually create the particle, and then you can actually see the particle when you look at things like scattering data and stuff like that. So again, resonance frequency isn't always something bad. Again, it's used a lot in things like chemistry, to be able to find particles or to be able to find the things that you're actually looking for, like alcohol groups or etc. But again, we usually think about resonance as some sort of bad thing. But again, when we're talking about engineering type things, it's usually some sort of bad situation. So again, this is Q factor resonance. Again, resonance is when the frequency then matches the resonance frequency. Again, the smaller amount of damping is, the easier it is to have some sort of resonance, which is going to give you a large oscillation. In that case, once you have a large oscillation, that gives you your resonance.